Welcome to This Explainer. We're going to shatter the illusion that tires are just simple chunks of molded rubber and dive into the brilliant engineering that actually keeps you safe on the road. I am thrilled you're joining me today because we're going to unpack the fascinating journey of how a modern tire is brought to life. So, what's the most complex piece of technology on your car? I bet you're instantly thinking of the engine, right? Or maybe the sophisticated hybrid battery systems, or that massive touchscreen infotainment setup sitting in the dashboard. But you might be surprised to learn the answer is actually the only part of your vehicle that physically touches the road. Tires have to strike this almost impossible balance between traction, comfort, durability, and energy efficiency. It turns out a modern tire is an incredibly complex composite. It's constructed from a carefully balanced recipe of more than 200 unique raw materials. We're talking everything from natural rubber harvested from the latex of rubber trees to synthetic rubber, specialized textiles, and high-strength steel. Okay, let's take a quick look at our factory blueprint for today. First, we'll look at the 200-ingredient recipe, followed by mixing and shaping, then building the green tire, entering the vulcanization forge, and finally wrapping up with 3D quality control. All right, Section 1, the 200-ingredient recipe, chemistry in the kitchen. Our very first stop is the chemistry lab. Formulating the perfect rubber compound is actually remarkably similar to baking a highly technical industrial cake. You can't just throw some rubber in a mold and hope for the best. In our recipe, elastomers act as the base material, kind of like the flour. Then we've got fillers, like carbon black and silica, that provide the necessary physical strength and abrasion resistance. We add plasticizers, like specialized oils, to improve processing, and protective agents, like antioxidants, to keep the rubber from aging or degrading under harsh environmental factors. But the real magic happens with the cure system. Just like yeast makes dough rise, the cure system is the critical chemical engine ensuring your tire can handle extreme physical demands. This package, typically involving elements like sulfur, zinc oxide, and stearic acid, is what ultimately converts a soft, plastic-like polymer into a highly stable, elastic rubber that can actually survive highway speeds. Moving right along to Section 2, mixing and shaping, prepping the ingredients. With our chemical recipe expertly formulated, we move to the mixing and shaping phase, where these raw materials begin their intense physical transformation. Everything gets thrown into this massive machine called a Banbury mixer. Now, this process has to be incredibly carefully temperature controlled. The mixer blends the raw materials into a homogenized, gum-like compound at temperatures reaching up to 170 degrees Celsius. But here's the catch. If it gets too hot, the compound can be accidentally scorched before it's even ready. So the whole mixture is monitored super closely before being formed into continuous sheets. It's fascinating how specific physical features, like grooves and sipes, are engineered directly into the tread. Different rubber compounds are actually extruded simultaneously to shape the tire's exact profile. And those specific shapes, they basically function like a giant water pump. Get this. A standard passenger tire tread is engineered to pump almost 4 gallons of water per second away from a wet road. That is absolutely vital for your safety. But a tire also needs a skeleton. Before we can build the actual tire, we have to reinforce our rubber by mechanically pressing it into steel and fabric cords. This is a heavy-duty process called calendaring. Fabric cords, like polyester or brass-coated strands of high-carbon steel, are pressed through massive steel rollers. This embeds them perfectly inside the rubber sheets to provide the tire's structural strength. Next up, Section 3, building the green tire, the assembly line. So we take all these prepped components, the extruded treads, the calendared steel, the inner liners, and piece them together into what the industry calls a green or uncured tire. This highly automated process uses a massive rotating flat drum. In Step 1, the machine lays down the airtight inner liner, which basically takes the place of an old-school inner tube, and wraps the body plies on the drum. In Step 2, the bead assemblies are positioned and the plies are folded up around them. Finally, in Step 3, the heavy steel belts and the extruded rubber tread are applied right on top of the whole assembly. The crucial point here is exactly how much strength is packed into this assembly. A standard tire contains about 1,400 textile cords. Furthermore, those bead wires we just positioned securely lock the tire to your wheel rim. Between the 4 tires on an average car, those bronze-coated steel bead loops provide enough structural strength, a massive 31,746 pounds of resistance, to effortlessly carry a 3,300-pound vehicle without ever losing their airtight seal. That's pretty wild. Okay, on to Section 4, the vulcanization forge. Heat, pressure, and transformation.
Now it's time for the forge, where our green tire enters a curing mold to undergo a permanent chemical transformation. Up to this point, the rubber is essentially just stuck together. It hasn't become a unified product yet. The assembled tire is placed into a massive mold, inflated against the walls of the mold, and then blasted with over 300 degrees Fahrenheit of heat. For passenger tires, this intense baking process lasts roughly 12 to 15 minutes.
This intense environment triggers a process called vulcanization. It activates that chemical cure system we mixed into the rubber back in the very first step. The sulfur permanently cross-links the polymers, bonding all those separate layers together into one unified, incredibly strong structure. At the exact same time, the immense pressure of the mold stamps in that complex tread design and all the identification info on the sidewall. Finally, Section 5, 3D Quality Control, the final exam. So, our tire is finally built and vulcanized, but before it ever hits the highway, it has to pass a rigorous final exam to catch completely invisible defects. Historically, this inspection was done manually or with 2D cameras, but traditional 2D cameras really struggle to see black rubber layered on top of black rubber, mostly because they require high contrast and are highly dependent on factory lighting. Modern high-speed 3D vision, on the other hand, utilizes laser triangulation. It's totally immune to ambient light issues and easily detects subtle volumetric flaws, making it infinitely more reliable. 3D vision really represents a massive technological leap, greatly expanding inspection capabilities. These systems measure the exact shapes, depths, and volumes of the tire. This guarantees precision and safety by catching tiny, low-contrast overlaps or blisters from the assembly process that the human eye or a simple 2D camera could literally never see. These highly calibrated 3D systems are deployed to scan for splicing gaps, folds, and geometric runouts. They even read the DOT manufacturing codes molded directly into the sidewall to track production data. Paired with X-ray structural checks and internal balance testing, this tech ensures that absolutely only flawless tires leave the factory doors. When you realize the immense chemistry, the mechanical engineering of weaving steel and fabric, and the laser-guided quality control packed into this one single product, it is just incredible to think it can reliably carry you for up to 80,000 miles. It's literally a symphony of science happening right under your wheel wells. So the next time you walk out to your car, take a look at those 4 black donuts and ask yourself, what other everyday miracles of engineering are hiding right in plain sight? I really hope this explainer gave you a whole new appreciation for the science of the road. Thanks so much for learning with me, and keep that curiosity fired up.